Good afternoon, everyone. Today we are looking at our last section from the last module in the last week of class. That is section 6.3, Taylor and Maclaurin series. We're going to describe the procedure for finding a Taylor polynomial or Taylor series of a given order. Well, a Taylor polynomial of a given order or a Taylor series, and what it means for about the remainder theorem. So we may talk about that. Notice I did cross off the last topic because we're just not going to have time to finish that. Okay, so what is a Taylor series? So a Taylor series happens to be a continuation of a power series. It is indeed a power series. And we can start off with a continuously differentiable function, f of x. I need it to be either continuously differentiable or it's eventually going to stop. So we want a continuously differentiable function if we want it to be a series. This function, if you remember, our power series look like some Cn times x minus x naught to the n. So this f of x equal to the sum n equals 0 to infinity. I need the nth derivative of whatever function I'm looking at. I'm going to divide by n factorial. And then, of course, again, I'm multiplying by x minus a to the n. This is a Taylor series expansion of a function, f of x, about the point x naught, which I used to have in here. I'm now letting equal a. Okay. So that is what a Taylor series is. And if by chance that a happens to be 0, so I can just make that a 0 and just get x to the n, it becomes a Maclaurin series. Any questions about the definition of the Taylor series or the Maclaurin series? Okay. All righty, so our first one, I forgot, I didn't change these. And this one is the cosine. It's funny how I got them backwards, but I got it right this time. All right, so this is what we have. So the Taylor series for sine of x, okay, so sine of x and cosine of x both have very nice Taylor series. They are about x equal to a equal to 0, and this should say the sine of x. Okay, so the sine of x is the sum n equals 0 to infinity minus 1 to the n, or negative 1 to the n, 2n over 2n plus 1 factorial, x to the 2n plus 1. So that is the Taylor series or the Maclaurin series, since it's about 0 for the sine of x. Okay. This is for the cosine of x. So it's Taylor series, otherwise known as the Maclaurin series, about this point is negative 1 to the n, 2n over 2n factorial times x to the 2n. So if I were going to write out the sine of x, I would get negative 1 to the 0 over 1 factorial, and then I would have x to the 1. The next term is going to be negative 1 to the 1, so it's going to be negative. I'm going to get x cubed over 3 factorial. The next term is going to be x to the 5th, and it'll be positive over 5 factorial. And the next term will be x to the 7th over 7 factorial plus dot, dot, dot. Okay, so this is the Taylor series for the sine of x. This is the Taylor series for the cosine of x. So I get that the cosine of x, again, I let n be 0. So I'm going to get -1 to the 0. That's positive. I'm going to get, that's just 1. I get 2n factorial. So that's 0 factorial, which is 1, and x to the 0. So I'm going to get 1. And then these are also going to alternate in sign, but these are all the even powers over 2 factorial plus x cubed, nope, x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus dot, dot, dot. Okay, so now you've been given 2 examples of Taylor series and specifically Maclaurin series for the sine and for the cosine. So the question is, how in the world do we actually find these things? And they're not that difficult to find. So we are going to derive the Taylor series for e to the x about our a being 0. All right, so in order to do that, okay, so in order to do that, I need to make a chart. So I would like you to also make a chart. All right, so that means you're going to derive the Taylor series for f of x equal to the function e to the x about a equals 0. So please commence on doing your chart. Okay, so hopefully by now you have completed your table. And let's fill it in. All right, so these first couple questions are going to be so easy. What is the first derivative? So if you remember, if I say the 0th derivative, that means I'm not taking a derivative. So I just want the function. So this is the function e to the x. N equals 1 means I want the first derivative. What is the first derivative of e to the x?
E to the x.
E to the x. And the second derivative of e to the x. And the third derivative of e to the x. The fourth derivative of e to the x. And the nth derivative of e to the x. Any questions? So this one is very easy. Now it says, oh, I forgot what I'm supposed to, oh, every time I do this, it messes up everything that I wrote. Okay. So now I want to evaluate the nth derivative at my a, which is 0. So e to the 0 is 1, e to the 0 is 1, e to the 0 is 1. E to the 0 is 1, e to the 0 is 1, and down here, e to the 0 will again be 1. So now what I need in this little square is going to be the nth derivative of my function evaluated at 0 divided by n factorial. Okay, So I'm going to take 1 and divide that by 0 factorial. So that's going to give me 1. I'm going to take 1 and divide by 1 factorial. That's also going to give me 1. I'm going to take 1 and divide by 2 factorial. So that's going to give me 1 over 2 factorial. I'm going to take 1 and divide by 3 factorial because n is 3. So that's going to be 1 over 3 factorial. I am going to take 1, because that's what I have, divided by 4 factorial, and I get 1 over 4 factorial. And if I keep doing this, this becomes 1 over n factorial. Okay. So here, I need the nth derivative at 0 divided by n factorial. And when I find my general formula for it, it looks like this. Okay, so my general formula. Okay. All right, so what did we have? We said we had f of x is the sum n equals 0 to infinity of the nth derivative at a times x minus a to the n, and that is over n factorial. Okay. So I get e to the x is the sum n equals 0 to infinity. I'm going to get here the nth derivative at 0 divided by n factorial, and x minus 0 to the n is x to the n. So here is where I need to make my substitution. Okay, so I need to substitute the nth derivative at 0 over n factorial. So therefore I get e to the x, whoa, is the sum n equals 0 to infinity. When I put in 1 over n factorial, I get x to the n divided by n factorial. And this right here, this is the Maclaurin series. E to the x. Although that's a good one. E to the x is a good one. It's not going to be much different, actually, now that I think about it. Okay. All right, any questions about that? Now, suppose somebody asks you to derive the Maclaurin series for f of x equal to x e to the x. All righty, well, again, I could make this table, go back here and make this table, put x e to the x, then do its first derivative, which is going to be a product rule, then do the second one, which is going to be 2 product rules, and then third one, which will be 3 product rules. So it actually gets bigger and bigger. Or I can see that this part is my e to the x. And that is also this piece. So I can take e to the x e to the x, and multiply x by the series we already know, n equals 0 to infinity of x to the n over n factorial. So that becomes the sum n equals 0 to infinity of x to the n plus 1 divided by n factorial. So now I know the Maclaurin series for f of x equal to x e to the x, because I just took what I already knew and I was able to multiply it. Okay, any questions?
Can you explain that again?
Okay, so I knew the Maclaurin, I found the Maclaurin series for e to the x. Instead of going through the long process of starting with x e to the x and then taking a derivative and taking more derivatives, what I did was I said, let's keep what I already know. All right, so let's keep what I already know here. And then I can multiply what we know by x. Since x doesn't have any n's in it, I can push it through the sum and make this now x to the n plus 1. So this now becomes the Maclaurin series for x e to the x without me having to do a table in order to get that.
Okay.
Okay. Okay, now we want to derive. Why is that so big? There we go. Okay, so now we want to derive the Taylor series. Now notice this does not say Maclaurin because my A is 2. All right, so if my A were 0, I couldn't do it, right? I can't do it about A equals 0 because f of 0 is not even defined. So I can do a Maclaurin series, a Taylor series, but it has to be about something other than 0. Okay, so again, this, let me just do it before I get started. This has to be nth derivative at, and this should be 2, divided by 2 factorial. Okay, so that's about 2. Okay. All right, so now we're going to do what we did before. We're going to start taking derivatives. All right, so this one is easiest if I take the derivative in this form of it being x to the negative 1. Any questions about that? X to the negative 1. Okay, so that's the function, 1 over x. I need to go straight down this column and take derivatives. What I am not going to do is simplify. I do not want to simplify until I figure out my formula. Okay, so what's the derivative of x to the negative 1?
Negative x to the negative squared.
Okay, so I'm going to get negative x to the negative 2, which I can write is minus 1 over x squared. Very good. What's the derivative of negative x to the negative 2?
Oh, x squared. Oh, shoot.
Each time we keep subtracting a number, keep subtracting 1 from the exponent. So the negative 2 comes down and hits the negative and gives me 2x to the negative 3. Just like any regular derivative of a polynomial, except it has a negative exponent. Rodney,
Yeah,
you see it?
yeah.
Okay. So this is positive 2 over x to the cubed. Okay, so Rodney, can you give me the next one?
Yeah. Is it gonna be 3x to the negative 4th or
Okay, so the 3 is going to come down and I'm gonna get negative 3 times 2, x to the negative 4. That is correct. And I'm gonna write that as 3 times 2, but it's negative over x to the 4. And I'm looking like I'm gonna need some more space. Here we go. I don't know why it's not moving. There we go. That's what I needed to do. Okay, so now when I take another derivative, the negative 4 is going to come down and give me 4 times 3 times 2 x to the negative 5. So now I get 4 times 3 times 2 over x to the 5th. Okay, let's add some more. I think we need a little bit more below. So let's do number 5. All right, so when I do number 5, I get negative 5 times 4 times 3 times 2 x to the negative 6. But this negative 5 times 4 times 3 times 2, that has a special name. What is that? When you multiply a number by all the numbers that are less than it.
Factorials.
Factorial. So this looks like negative 5 factorial over x to the 6. Okay, so can anybody tell me what this next one would be? What's the next derivative going to be?
negative 6 factorial and then over x to the 7th.
Okay, is it negative?
The negative 6.
So we had
Negative, right?
positive, negative, positive, negative, positive, negative,
Oh, it's gonna be positive. It's gonna say positive.
positive. Good, 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 good. Okay, so we can see that all the even numbers are positive, all the odd numbers are negative. So that screams to use a negative 1 to the n in the problem. Okay, so can anybody give me what they think is the nth formula for a general n? I have 6. So I have 6 factorial, 7. I have 5 factorial 6. All right, can anybody see a pattern? So if I have n, what am I going to have?
I think it's -1 to the n multiplied by n factorial, all divided by x to the n plus 1.
Okay, that's perfect. You can't get any more perfect than that. The -1 to the n is what's causing our numbers to go negative, positive, negative, positive. And then our n factorial represents everything that we've gotten before in the numerator. So they all look like factorials. And then whatever the number is, if it's the nth derivative, it seems to me like I'm getting x to the n plus 1 in the denominator. So I now have a general formula for the nth derivative of the function. Does everybody see that? It might have been hard to see if I was multiplying it out, but when I don't multiply it out, it makes it very easy for me to see. Okay, next column. I need to evaluate everything in the first column at 2. So I'm going to get 1/2. I'm going to get -1 over 2 squared. I'm going to get 2 over 2 cubed. I'm going to get -3 factorial over 2 to the 4th. I'm going to get 4 factorial over 2 to the 5th. I'm going to get -5 factorial over 2 to the 6th. So can anybody give me the formula for the most general, what's the most general formula? Only one thing has changed. What's been changing? It's really just x.
Is it gonna be -1 to the n and then n over factorial, sorry, over, is it just 2 and then n plus 1 to the n plus 1?
That's correct. Okay, any questions how we did that? Any questions of how we did that? Okay, so now I know the nth derivative at 2. And you know, in the last class, I actually went through every single one of these blocks. I did. I went through every single one of these blocks. But I just realized that I don't need to go through all of those blocks. Once I get this, all I need to do is take that and divide it by n factorial. Why does that say 2 factorial? That should say n factorial. So therefore, we're going to skip this part because I just realized we don't need to do all that because we have a formula. We can come right down here because this is the nth derivative at 2. And what I need over here is the nth derivative at 2 divided by n factorial. So that's going to take a -1 to the n times n factorial divided by 2 to the n plus 1 And I'm going to divide that thing by n factorial. So when I put the n factorial there, what do we see? Aha, the n factorials divide out. So now we get that the nth derivative at 2 divided by n factorial is negative 1 to the n divided by 2 to the n plus 1. Okay,
I have a question.
yes.
When we have to divide by n factorial, wouldn't it be, since it's already in a fraction, would we have to multiply by the n factorial?
No, because we're dividing by n factorial. So dividing just means put it in the denominator of what you already have.
Okay.
Okay. Okay, so now we have f of x is the sum n equals 0 to infinity of the nth derivative at a divided by n factorial over, so I'm sorry, times x minus a to the n. And we know a is 2. So I get e to the x, the sum n equals 0 to infinity of the nth derivative at 2 divided by n factorial times x minus 2 to the n. But
Are we still looking at ETX or 1 divided by x?
oh, I'm sorry, you are so right. Thank you, thank you, thank you. Oh my goodness, yes, thank you, thank you. Okay. All right, so now I'm just going to replace that. So I get 1 over x is the sum n equals 0 to infinity. I get minus 1 to the n divided by 2 to the n plus 1 times x minus 2 to the n. And I'm going to simplify that and make that look real pretty. So I have 1 over x is the sum n equals 0 to infinity. I'm going to pull out the 1/2. And I'm going to write it as x minus 2 over 2 to the n over 2. That whole thing gets raised to the nth power. Okay, so you see the minus 1 to the n, the x minus 2 to the n, the 2 to the n, and then the other 2, which makes it 2 to the n plus 1. And I don't like the fact that it looks like my numbers are floating. So there we go. Okay. So that is the Taylor series. X equals 1 over x about a equal 2. Okay, now here's the thing. I don't know if you recognize that, but that's a geometric series. So I can write 1 over x is the sum n equals 1 to infinity of 1/2 times negative x minus 2 over 2 to the n minus 1. So here, A is 1/2 and R is the negative x minus 2 over 2 to the, oh, that's it. That's R. So now the geometric series, this converges. Absolute value of R less than 1. So I get the absolute value of the opposite of x minus 2 over 2, which is just the absolute value of x minus 2 over 2 is less than 1. So that gives me the absolute value of x minus 2 is less than 2. And this number has a special name. Does anybody know what that name is? That's radius of convergence. Okay. So let's find the interval of convergence. I get -2 is less than x minus 2 is less than 2. So my interval of convergence turns out to be 0 less than x less than 4. So if it goes outside of that interval, it will not converge. Now you can find other expansions for 1 over x about other things. Tomorrow, I'm going to do a Taylor polynomial, and we're only going to go maybe like the first 3 or 4 terms, because this thing really does not have a formula, the one I'm going to do. So we're only going to do like the first 4 terms, maybe even just the first 3 or 4, and get a Taylor polynomial. That means it's going to stop. It won't be a complete series. Okay, any questions? Okay. That's it for today.